Thank you. I'm Jeff Hodges. I work at a little company called Twitter. I have been there for the past 4.5 years, and I'm going to be talking about distributed systems. There are a lot of reasons that you should listen to me when I talk about distributed systems. I have gotten to grow up with Twitter. When I first started, we were 120 people all told. We are now 2,400, 2,500, something like that. And along the way, we had to go from a monolithic Ruby on Rails stack, affectionately known as the monorail, and to a distributed multi-DC, multi-service architecture. And along the way, we did it in about 4 years, which is kind of faster than you'd like to, especially at the growth rate we went. And those things that we learned, oh, hey, man. Oh, cool, this has totally just stopped working now. Hey, there we go. Boom. This is why you should listen to me. Along the way, I've had a lot of different hats. One, I worked on our storage layer back when that meant integrating in Ruby, trying to get Cassandra in our tweet store, which did not go well. I have worked in this thing called trust and safety and anti-spam. Trust and safety dealt with most of the legal stuff that I'm not going to talk about because it gets a little hairy. And the other half was anti-spam, and we did a lot of cool stuff on Mesos and Cassandra and other data stores, Manhattan now. And most recently, I work on TFE. TFE is the Twitter web server that handles almost all the web traffic for Twitter and related properties. I worked and shipped forward secrecy at Twitter, which is a kind of a cool project that I'm not going to get to go into detail today. But it's a bunch of crypto stuff that I've been doing for the past 6 months or so. So you should listen to me because I've done a few different things and I've seen some things, and those might be useful and informative to you. Of course, there are plenty of great reasons why you shouldn't listen to me. For one, I worked on a rocket ship. And it was a rocket ship that we had to take from a biplane into a rocket ship while we were still flying it. Kind of not easy, and that's not going to be normal for everybody. And not everybody's going to have thousands of machines and thousands of users, millions of users, and making that all work. So there are plenty of reasons for you to take what I say today and figure out how it works for you. However, one thing that I've worked on really hard in this talk is to be scale-invariant, that these lessons should at least apply as well to the 3-person company as it does to the 300, 3,000, 30,000 company. So we're going to talk about building and running distributed systems here, what it takes to think as a distributed systems engineer, because all of you are in this room. I'm now giving you the title of distributed system engineer. It does not mean much, but you can say that. And we're going to talk about, to do that, we're going to talk about a quick foundation. The foundational stuff is what makes a distributed system different than other systems. When I was interviewing long ago at various whatever, I would get asked that question, and I would kind of hem and haw and say something like, well, there's a lot more latency and stuff, and there's things that happen, and they're like, okay, yeah. Well, okay, you don't know what the hell you're talking about. I'm like, oh, hey, all right. And what's different is that failure is much more common in a distributed system. It's so common, in fact, that you will have to write things differently. Here's a quick subset of various things that I've seen in my time working on distributed systems. You have garbage collection spiral on a single machine that causes it to just time out. You can have a TCP connect timeout. If you're familiar with the BSD socket API, oh, by the way, you should learn about that. Connect timeout, so a process starts getting overloaded, and then so the client somehow gets stuck to it, they keep going back to that one machine because the TCP socket timeout is so long that they actually can't even connect to it, but they're trying for a really long time. You'll also see things like socket writes succeed locally, but they fail on the remote machine. This is also known as the MongoDB problem, which is where you write some data and it says, yep, got it, go for it, but you don't know that it actually got to the other machine successfully, or if it did get to the other machine successfully, you don't know that it actually did the right thing at the end of that. And that's a real problem. That's a subset. You can also have all sorts of good stuff. Master elections not working because whatever, or your master database just is overloaded, and so everything crumbles. And what's interesting about these failures is that they're partial. That distributed systems have this idea of partial failure, separate from what single machine systems have. Single machine systems, typically, when you start having an unlock fails in your mutex, that means the entire process needs to die because it's invalid, it's crashed, it's done. When you start talking about distributed systems, you can't, a single machine going down won't take down and shouldn't take down the rest of the system. So now we're going to so that's like a foundation that we've got. Like there's this idea of partial failure, that things will go wrong, but the entire system overall will continue to move forward. That data will flow. And someday you're going to have another engineer or a PM or, God help you, a user come to you and say, hey, the thing is slow. And you go, what do you mean thing? And you're like, they go, well, OK, so tweeting or search, getting a search result back is really slow. And why is it slow? And you go, oh, OK. Let me think through the 12 different systems that it could be, multiplied by the 3 to dozen worth of subsystems inside of each one of those, and let me figure out what you mean by it's slow. And that's tricky. That's really hard. It's hard because it's delocalized. There is no one place where it's slow happens. And so you have to figure out, as a distributed systems engineer, the kind of techniques and tricks to understand the gestalt, the overall behavior, and be able to pull in and get the specificity that you need. And so to that end, metrics are the only way that you can do that. We'll talk about the alternatives a little bit later. Metrics are the idea that you should expose in each process that is running what it's doing. You have a counter that says, how many tweets have I ingested? How many search results have I seen? What is my 99th percentile of latency when talking to the database? And what's really cool is when you do that to another service, and then you compare what that service thinks is happening and what your latency looks like, and what you think, and you can do really cool tricks with that. Because you want to start getting time correlation. There are too many machines, even at a small number of 3 engineers, like to be able to get a look at log. We'll get to that later. You want to get time correlation between metrics in order to figure out what's going on, and so that you can look to see if it's one machine that's having a problem. Is it all the machines that are having problems? Is it the latency on some other system behind it that's causing the thing? Your alerts may have fired, but maybe there are alerts on someone else's system that should have fired but didn't, or they just didn't write them. And so you need to know whether it's the things that you own or the things other folks own, or whether it's this A or B or whatever, and you can't do that but at a glance using metrics and having charts and graphs and pretty little things and having a nice overview of the whole system. It's also key to have a standardized way of getting metrics out and reading those stats. That's really helpful across your DC because as you grow the number of services, you quickly run out of mental space to know what all the services are. There's that old quote about distributed systems are when a machine you don't even know existed can cause your system to crash. It's totally true. It's an accurate thing. And that's going to happen even at 3 people because you're going to have systems everywhere, and you won't know what they've been working on. So folks sometimes say, well, OK, if you care about performance, you should just do a profiling thing. We should figure out profiling. OK, so here's the problem with profiling. One, it is a snapshot in time. You typically run it for some period of time because the overhead is pretty large, and then it moves forward. And you get a snapshot and some overview of how much CPU time it takes, or if you're really lucky and the profiler is really good, you get I/O time. But that's not great, because what you actually have is the problems that show up in distributed systems tend not to look like what shows up in a profiling. What will happen is they are either transient, which means they only happen once in a while on maybe some machines, which means that you need to be able to go back in history to figure out the problem. And so profiling from time A to time B doesn't really matter if time A minus 20 was when the problem actually started. You also need to be able to the profiling also doesn't give you these weird aggregates where they're super high of percentiles, but that usually isn't necessarily mapping to what time you're actually seeing users have involved. Kind of crazy. Anyway, so the nice thing about metrics is that you can reapply them. And one of the nicest things about metrics is that you can actually know what your deploys are doing, what your releases are. Because you actually need to, as you go into distributed systems, you need to start being able to track things like, OK, cool. We did a thing that was supposedly faster. And because distributed systems are large and have a state space, a space of states that they can be in that are much larger than single machine systems, you want to track that that thing that you thought was going to make it faster for everybody didn't make it faster for the cases that you thought of, but they made it slower for everything else. And you're going to do a lot of these things. You're going to do releases all the time. And you're going to do metrics changes all the time. And you can even, that's even as boring, if it's stuff that you're not ready to release yet, it's as boring as having the git SHA or the SVN revision or whatever, like as a commit, as a stat in one of your metrics. That turns out to be really handy because then you can find out when your deploy scripts suck, or like you just forgot about one set of machines, and you can just look at a graph and go, oh, all the version numbers are the same here except for this one. It's really handy. So at the very least, you can do that. Folks will talk about logs, but logs lie like a lot. And what I mean by logs is free-form text logs. They are the godsend to kernel hackers and to like single machine systems owners because they're great. You can like copy them around and you can look for stuff. However, there are a couple of problems that get much worse in distributed systems. The first one is that common problems get overlogged. This happens in literally every system I've ever looked at. There's these things that are like exceptional, sorta, kinda, like there was the zookeeper path didn't exist. This is a thing that happens in TFE, but we actually don't care about that because that just means that, anyway, but it gets logged and it's not super useful, and people have these stacks traces or just messages that just like come up. You can look at a kernel boot process, right, and you get all those cute little warnings, warning, colon, whatever, and then you're like, I don't actually give a fuck about the USB PCI stuff because I don't use it, right? And that same kind of stuff happens in distributed systems, and you just don't have mental space to clear out all those things because you're doing a lot of work. You'll also have that the uncommon ones, the ones that you might actually care about, get buried in all those messages. I have seen incidents take forever because the only thing that we had was logs, and we just didn't see the one log line that said, hey, yo, everything's foobarred. Like, good luck, right? And then the last point is that, like, the reason why edge cases cause bugs is because you didn't think of the edge case. If you had been doing really good logging and been able to log enough data to get the edge case, there's a pretty good chance you had thought about the edge case and would have written the right code for it, right? So you don't want to do this. What you want to do instead is you write metrics, and then you write metrics that are correlational, so that even if you forgot to put static metrics into subsystem B, if you look at the numbers at subsystem A and they're at this height, and you look at the stats in subsystem C and they're down here, you can pretty much probably tell that subsystem B in the middle is the problem. Or at least you can do some magic there. So now we're going to that's cool about metrics, and we're going to talk about avoid coordination. I don't have a good transition for that, so fuck it. Human beings have this idea of what consensus is, because we get into a room and we take a vote, or we all agree and have a conversation about it. But it turns out our idea of consensus is extraordinarily rough and incomplete. And so when we start looking at the mathematical basis of coordination and consensus, getting computers to agree on literally a number is very, very hard. And so you will have these algorithms like multi-Paxos, Paxos, and then the lesser ones like 2PC, 3PC, gossip protocols. They're all designed with just the idea of getting computers to agree on numbers, right? That's it. And that turns out to be really expensive and hard. And the more coordination that you have to build into your system in order for it to work successfully, the harder it is to do so. Avoiding coordination is another word for horizontal scalability. So what you're trying to do is trying to find the right places in your app that you need to coordinate on in order to split up work effectively. That's why you don't use Zookeeper as like a system of record for all of your tweets, but you probably would use it for like your host list or various other distributed locking things. And one of the reasons that coordination is hard is because, like, as I mentioned before, if your mutex unlock in a single machine process just fails, you know that the process is corrupt and you can just kill it and restart it. But in a distributed system, because switches go down, garbage collection happens, things just get wonky in weird ways, I/O takes too long on a disk, you can have a mutex unlock fail just automatically. And you actually have to build that into the protocol and then communicate back and forth across many machines that like failure occurred and we're going to retry. And so you want to break these things down into subproblems. And what's really cool about subproblems, as we know in engineering, is that you get easier problems. So if you can fit your problem in memory and you're a distributed systems engineer, you're done, game over. You don't have to worry about it. Now, obviously, there's definitely some kernel hackers in this room who are kind of mad at me right now because I've said that if it fits into memory, it's trivial. All right, don't worry about it, don't worry about it. That is that we're talking about at the scale of like having many machines. Of course, there are problems that you will have to solve like in the bottom layer, but for us, there are B-tree implementation, like RockDB exists. All these different pieces already exist on a single machine, and they've been tested for, I mean, send-mail exists if you, or post, Linux exists already, so we don't have to solve that problem. Distributed systems are unusual in that only for the past 15 or so years have we really had to really connect with what a distributed system works at in the industry at large. There are obviously like HPC things that happened many, many years ago, but that's not been most of us. Nowadays, it's almost all of us. And when you're building a distributed system, you want to build in this idea of back pressure. Back pressure is a really great idea. I love public infrastructure a great deal. And so back pressure is a cool idea from plumbing, which is they have to go from these giant pipes of water into these little pipes of water that are inside of each of our homes. And so how do you deal with the fact that that big pipe of water is A, a lot of water, and B, can fluctuate and change over time? So what they do is, in plumbing, they build this idea that they will design the system with little weird nitbits and things and gauges and stuff like that, such that when water gets too high a pressure into those smaller pipes, it actually gets pushed back out. And you do that inside your own distributed systems. Because it turns out, just like those little pipes have a certain amount of water that they can handle all at once, our software only has a certain amount of resources that it can use at a certain time. That's why, I mean, we all use Turing machines, but they have a physical memory that they can't go past. That's why U-limits exist. There's a certain amount of CPU that you have in each machine. There's a certain amount of disk I/O that you can get, which is way less than people think, unless, yeah, it's complicated. And then there's network. And so you actually have to like build in this idea of like how many messages can your system handle at once. TFE did this recently. We have this weird two-process system that we use. The first does like encryption, decryption, some other really fancy stuff, and then like standardization. And then we have the router process. The router process, unfortunately, currently is a little bit less efficient than the front-end stuff. So when we pass data back to it, if we pass enough, the router can just crumble, and we will just GC kill. Like it would just die from OOM. Really bad story. So what we did is we added like, okay, cool. There's literally 20 messages, 20,000 messages in the router at once. We can't handle anymore, and we're going to return a 500 for all of these requests. Boom. What's really cool about that is that means that it would also fail on the health checks that we were getting from the LBs, and the machine would get taken out. It took some incidents that would have taken probably 10 or 20 minutes to figure out why this one machine was causing problems, or that it was one machine, into a 7 seconds later, as soon as it started having problems, it was out. Which was really great because there were some deadlocks that showed up about 3 weeks after we wrote that in the Zookeeper client, and we had that happen to a couple of machines. Fun story. So let me get more concrete with the back pressure stuff. Some examples of it include dropping new messages on the floor. This is great if you actually don't care about them. Usually if you're going to just drop messages and not tell anybody, you want a stat that you can anchor and say, hey, yo, this is going up. And then you have an alert saying this changed in the past 5 minutes. And then you know about it. Because that means that your system can't keep up. And if you can't keep up, you're screwing up. The TFE example was an example of the second one. We return documented overload errors so the system clears through a stat as well, yada, yada, yada. I'm returning 500s. And then the final stuff is, they're not quite back pressure, but they're close enough that they fit into the slide. Another resource that you have is your user's attention, your client's attention. And that means that you need to only spend a certain amount of time on each of the processes, give it a timeout, maybe an exponential backoff for connects, that kind of stuff. You can just Google these things, you can find a ton of it. And that's important because it's difficult it is better to fail early and maybe be able to recover than to continue to accept work and then not be able to respond to anybody's work. And often I've seen many, many systems who are like infinitely scalable, and they just kept taking messages, and then we had to discard all of that data. Like we actually just straight up, like I've seen this at Twitter and at previous jobs, where like stuff that didn't have back pressure kept accepting messages, and then we had to kill them off because they literally just couldn't recover, and we just lost data. And that was just a thing that happens. And you'll have that in your systems until you're thinking about these things. And so now I've been really depressing, so let me talk about the flip side of partial failure. Because the horrible thing about partial failure is that everything fails all the time.
But the cool thing about that is that you can build systems that don't care about it. You can build the idea that like if a machine goes down, we don't care. We will continue making forward motion. And what's really cool is you can build neat products out of that. One of the greatest examples of a partially available system is any given distributed search product. Not all of them do it great, but this was, I think it was Inktomy that it was the first ones to talk about doing it. And then since then, the Goog, Yahoo, Twitter, obviously, everybody does this, right? Your search index, which is just IDs and document IDs, right, and like search terms, doesn't fit onto one machine anymore because it's really big. Maybe you like went to some big data conferences and you learned how to write a web crawler. I don't know. So you split it up across many machines. You split the index. You pick some partitioning strategy that makes sense for the data. And you now have like 1 to 5 machines. And when a user's query comes in, you have a system that goes, OK, cool, this little muxer deal. I'm going to actually query all of those indexes individually. And then I'm going to take their results. And each of those indexes are going to return their most relevant results. And from their most relevant results, I will sort them all together and take the most relevant results from all of them, right? And send it back. What's really, really cool about search and why people love talking about it in distributed systems is that you can knock one of those machines down completely. And you can actually still get really good results. If your partitioning strategy isn't super crazy, you only lost 1 over n of those documents. And so you don't have to like fail the request and return a fail whale. You just return a slightly less good search result set. That's it. That's really nice. So that means that you can do really cool tricks, and you can start being a little bit more risky with the kind of products that you build out. Because if a machine goes down, or if you're doing a rolling restart, maybe you get a little wonky stuff sometimes, but it stays up. People don't notice, and you still make it, you know. At the end of the day, you're kind of trying to make money, so you can just still make money off that. That's a really good example. Oh, the also cool thing about search is that search engines that are really good, they will also set a certain amount of time that they're willing to spend on a query, which is really helpful when you start having slow disk problems, like the disk is going bad or it's being eaten up by some crazy runaway process. And so they'll actually put a timeout on how long it will spend on a search result scanning through memory or disk before, and then it will just return whatever the most relevant results it was able to find at the end of that timeout. Pretty nice. So you can do this all the way down. And that's really, really important because it turns out that human beings notice, they start being able to notice things that happen at 100 milliseconds. So if you can do it in less than 100 milliseconds, you're golden. If you take about 100 milliseconds to a second, let's call it 750 milliseconds, you're OK. People won't be too annoyed. But at like a second, or certainly 5 or 10 seconds, people are no longer paying attention to your tab, and they're no longer looking at your web app. And so if you can't do something in less than a second, you're kind of not doing great. And so it's important to be able to do timeouts. Who to follow was an example, was one of our very, very first systems that we built at Twitter that was separate from the monorail, but in the like read-write path of like actual production, right? And we didn't know shit about 4.5 years ago, and we were trying to figure out how to make this all work. So what we did was we gave it it was having some performance problems as we rolled it out. So we gave it a pretty high timeout of like 2 to 3 seconds. And the monorail overall gave like 5 seconds to each request before it would get a 502 return. So a couple things happened. One, when who to follow went down hard, we would just serve who to follow is that little doodad on the top left, I think it's on the top left, of your like home timeline, and it just says who you should follow because we think that they will give you engaging tweets. And it's really nice. It's really nice. It was good features, very engaging. People liked it a lot. So when who to follow would go hard down, we would return whales for your home timeline because we couldn't satisfy that little doodad up there. And then when it was getting slow, because we had a 2 or 3 second timeout, it would reduce the timeouts for everything else to 1 or 2, 2 or 3 seconds. So now we had less time to do everything else because unfortunately Ruby is a one operation at a time kind of process, and so you don't get a lot of. So when you start eating up all the time on one type of request, or just you have to do a flat map or whatever, you run out of time to do everything else. So we would serve whales for reasons that didn't look like who to follow, but were related to who to follow.
So let's talk about partial availability. Partial availability in this case is if who to follow doesn't return you a result or doesn't return you a result in time, don't show the doodad. That's it. Boom. You have built a distributed system with partial availability. You have a completely optional sub thing on your web page that you actually don't need to show, and it does not need to be there. And so if it doesn't return, no biggie. And so what we did was we reduced the timeout dramatically. It's like 200, 300 milliseconds. That's still a little high, by the way. But it gave us a lot more room, and if it just was hard down, we just didn't worry about it, because it was just coming back, and somebody would get alert fired, and nobody cared. That's great. And finally, I'm going to talk about private messaging databases. All right. See, the cool thing about being a distributed systems engineer in 2014 is that the architectural ideas that you come up with actually impose constraints on the product itself. For instance, let's suppose that you have a private messaging database and you're doing a DM type thing, or you're doing Facebook messaging or whatever, right? And you have to decide as a distributed systems engineer, if enough machines go down, does that mean everybody loses some of their messages because we have partitioned the database by message ID? Or do they lose, or do some small subset of users just lose all of their messages and that is now unavailable for some time? Or is it that they are like per conversation? Those kinds of things, right? And that's actually really important because they imply very different product goals and very different product constraints. And that comes at just like a low-level architectural stuff. And picking which partial availability you want to go for, whether it's like how many messages going down or users disappearing, is just a choice you have to make. And more choices you have to figure out is how to deploy code and restart the process without actually releasing it. Flickr was the first ones to really talk about this in detail. There is this idea of a feature flag. Yeah, right. And they talked about it originally. Well, people originally understood feature flags as being related to A/B testing. You had a user interface A and a user interface B, and you wanted some percentage of users to get A versus B. And so you would build this feature flag system, a way that basically is just an if statement, saying whether a user was in bucket A or bucket B. And you give them different UIs for each one. What's really cool about this idea is that you can actually roll out your infrastructure with feature flags. You can actually take this very idea and slowly move users to new subsystems, new systems, new entire code paths, without actually having to do a deploy. Because it turns out deploys take a while, even for 3 or 4 machines, sometimes even longer at 3 or 4 machines, because you can't restart all of them at once. And doing rollbacks gets really hard and all these things. So let me be really, really specific here. Let's suppose I have seen big bang rollouts where we have scheduled April yada yada Thursday afternoon, and we are going to do a big bang rollout of we're going to move everybody from this crazy database that we had, and we're going to move it to this new user service that we rolled out. And the code's gone through QA a couple times. We put it in a staging environment. It looks all right. And then you roll it out on that Thursday afternoon, and it goes fucking haywire. Like, it either is just like broken, data's coming back funny, or there's just bugs everywhere. The performance just drops like a stone. And then all of your Opsy folks, whatever you call that at your company, get mad at you because they're like, what the fuck didn't you do QA? And you're like, yeah, but. And so what do you do instead? Well, what's cool about feature flags is you can actually like roll out a system and then shut it off because you have a knob with a percentage saying how much % traffic should go here. And you can partition it on users and like have user IDs as like the random number that goes in, the modulus. Or you can have just random traffic if you don't have the user ID. What's really, really cool about this is that you get slow, dark rollouts. You can do, OK, cool, I want to start sending reads to this new system, or writes, but I don't actually want to use that data in the response going back to the user. And so we will make the normal reads and writes for the old system, but we will have this little feature flag that we've cranked up to whatever percentage, and it will drive reads and writes over there. And then you can crank it up as you're like having scaling problems in the new system, because they always happen, because you just have bugs. Bugs just exist. You can identify them and then just turn it off. Well, and just iterate on the user service with actual live production data, because there's nothing like production data. There's just no behavior like it. You can totally replicate things and you can make a thing happen, but there's just nothing like production configs. What's really cool about it too is that you can keep adding feature flags. You can start with dark read and a dark write, and you can add a dark read comparison flag, which has been critical for a lot of systems that we've been doing, because we've been doing these rewrites, where you go, okay, user system, the old system returned this value, and we've queried the new system, and so we have both their data sets, and now we will compare the two that came back and see whether or not they're the same. And then you can like find these really, and then if they were not the same, you log it, and you add it, and you click a stat, and you say how many requests were successful versus failed, and yada, yada, yada. And it's great, because you can now take these big bangs that usually involve like a massive rollback procedure, or a 6-week to many months time period of just having awful bugs that you didn't even know existed, into something that is ongoing and moving smoothly with no stress, no emotional ties. There's no like people getting angry at a Friday post-mortem. You just handle it. Now, folks that are classically trained object-oriented programmers or new engineers coming out of college or wherever, sometimes they look at code like this. The decider is the one, what we call our feature flag system, and they get kind of cranky, because there's going to be a few of these in your code base. You try to reap the old ones, but sometimes people forget. But mostly, they have problems with just how it looks, because they have different code, or there's multiple things going on in one method. You're like, yeah. And you can do some tricks. You can make policy objects. You can pass a lambda in to make some of the stuff easier. But at the end of the day, we're distributed systems engineers. At the end of the day, we're making the trade-off between local complexity for global resiliency and global simplicity. And that's the spectrum we're working on. And so these if statements, you just got to get over them. Like, they're just, I have seen a bunch of attempts to like just not have if statements, and they just exist. And they will happen. And that's okay, because we're engineers, and we get paid to like actually understand what code does. And there is, like, oops. Which is something I didn't get a chance to talk about in the metrics section. I want to briefly touch back on that. Metrics are how you cross the mental gap between what you think your code does and what it actually does in production. Those are very different things. Even today, you think your system that is working just fine, you think you have an idea of what it's doing, and unless you have metrics telling you that it's doing what you think it's doing, it's probably not doing it. It's probably not. The cool thing about feature flags is, man, I'm coming up on 11 minutes. All right. Feature flags, plus other things I've been talking about implicitly, imply that multiple versions of everything are the norm. That means multiple versions of an API, multiple versions of the data itself, and you got to start doing backfilling and shit like that. There's also multiple versions of code at any one time. People deploy canaries to see if the new thing is going to work, and they like have metrics and alerts so that they can actually like figure out if it was really bad and take it back. But this is the norm, and we can't. The idea that there is a single source of whatever is just not true. And that's okay. It's okay. It's really okay. We just got to get past it. Like, this is a whole new world that we have to deal in. A couple more things. We have exploiting data locality. Data locality is, some people know about it in terms of single machine systems, but we're going to talk about it in distributed systems as well. It's the idea that it is better to work on data that is together on one machine and nearby on that one machine than it is to go across many machines. Why is that? Okay, well, it turns out that dereferencing a pointer on one machine doesn't fail nearly as much as dereferencing a pointer that actually is an object on some other machine somewhere in the universe. That's why all those crazy ORM things and like all those objects, oh, I'm not even getting into that religion, but it's just faster and easier to understand data that works together. What's cool about that is that not only is it in space, because you want the data to be together in space, there's also data locality in time.
And so one of the great things about this is like, if you know how a CPU pipeline works, like how a process works, you know this already is a thing because you know about L1, L2, and now L3 caches. This world is amazing. But you know that like computers work really well when you keep asking them to do the same things, or even better, work on the same data over and over and over again, all together at once. Which is why batching is awesome. You remove a bunch of overhead of like the network transport. You also remove a bunch of like setup and teardowns you eventually have to do anyways. There's also this idea from CDNs that is really, really great called collapsed, request collapsing or whatever. And that's the idea that it's not caching, let me be super clear, but when multiple requests come in for the same data, you actually only need to serve one of those requests if they're all happening right together. If you already have a request in flight to a backend system to bring that data to you, you actually can just hook in the rest of those responses to that first request while it's live. Because you're not going to get any fresher data, any better data than the rest of those. They all came in and you're going to return it. So it's great. We should do more of that. That's a thing that CDNs do all the time. That is, let me be super clear, is not caching. We're not talking about caching. It is requests in flight. It's super great. We should do more of it. Also, computers are fast. There has been a lot of confusion and a lot of misinformation. I'll just call it misinformation about how fast computers are. I have seen a number of runtimes that I will not name who are super excited when they get to 250 requests per second per machine, and that is fucking intolerable in 2014. You can do thousands of requests per machine. This is trivial. For like a CRUD web app, like a stupid web app, create, read, update, that kind of stuff, destroy. You can do thousands of requests per second, per machine, with latencies on the order of hundreds of milliseconds. That is easy. That's trivial. That's actually, this is so a low bar of what you're able to do in 2014 that I should have multiplied all of these, multiplied thousands by at least 10 and divided hundreds of milliseconds down to single milliseconds. And if your runtime can't do that, it is horse and buggy bullshit. You are working on technology that is 20 or 30 years out of date. It shouldn't exist anymore. We shouldn't be using it. You are contributing to global warming and climate change. And on top of that, your users kind of fucking hate you because you have to spend all this time, like they're waiting on their request to come back, and you're so busy operating with your like 20 billion machines when you could be doing them on like 3, instead of like doing real work that gets them features. This is just bad. It's just bad. Okay. Oh boy, 7 minutes. So the implicit thing that I've been talking here is that extracting services over client libraries is a good idea. That having a monolithic web app is not necessarily the best thing in the world. Certainly you can make it work. It usually involves rewriting your runtime into a different runtime. But one way to there are a lot of things that get solved if you prefer building out new features by breaking out services instead of writing new client libraries to talk to a like really dumb database but do smart things in the client, right? So what are the things that you like avoid? Well, stricter boundaries between the client and the server means that there's less cheating. That means that there is less, when you start trying to build those like fat clients that do a lot of work for you, people will start relying on the internal details of that client inside their process. And they will you will just, and sometimes accidentally have somebody who decided to reflect down into the guts because they needed a performance improvement or something in order to do that. And you just can't do that when you have a network switch away. That's an extreme example, but there are a ton of more common examples that people just cheat and they don't do the right thing. And then when you need to change them over to a new version of the fat client stuff that maybe does things completely differently underneath the hood, you now have to go spend all that time. So there's also the pulling out of services makes deploys easier. Those of you who are familiar with having to disconnect your MySQL connections before making schema changes and other things and knowing how like warm-ups against databases or just files on disk, you know that your boot times start getting really long, especially if you have to do like warm-ups for a file on disk. And so by pulling out to a service, you make that a couple of VMs who have to do that on their deploys, but the rest of your systems, the many more systems that you probably have don't have to worry about it. They just have a service that they're querying, and it provides like the same kind of like HTTP JSON or Thrift API forever. That's really great because it makes deploys easier. It means that you don't have to hire like a whole like release team that all they do is just deploy your giant monolithic thing and then have everybody. I've been in these the 10 in the morning, what are we going to deploy today meetings in which the infrastructure engineers, typically you, are like swinging their big giant egos about like, well, my change is going to be scalable, and like we fixed all these things, and then the product people are like, yo, yeah, but we actually need to like, I haven't shipped in like 3 weeks. Can I get a deploy in? You get rid of all these things by just breaking out your deploys, making every deploy easier. Last thing is something I hinted at before. If you avoid human coordination by doing service instead of libraries, because once you start having, because you're still going to have a bunch of code repos, like that's going to still exist, because you're going to have like admin things are going to have to happen. You're going to have a revenue system that needs to talk to users, or while your production system talks to users, and there's just going to be a lot of things. There's going to be batch stuff on the end that needs to get access to stuff that's only available live, and so they're all taking a copy of this giant fat client library, and you have to upgrade everybody anytime something breaks. And that means that like instead of having a nice strict API that you've built and designed as a service, and knowing and getting those other teams to migrate with you, and because they are typically involve a lot more cheating when you have a fat client library, it gets really, really hard. You have to tell everybody that, hey, yo, we're going to radically change like how we do MySQL databases. It won't change the API, but I need you to upgrade so that we can do all this work. And distributed systems engineers tend to work at companies, well, their priorities aren't going to be your priorities. Even at like 3 people, you're going to have somebody who's like, no, I'm not going to do that because we don't have time to do that right now. So we're just not going to make that change. And so now, the thing that you would be a really obvious, like, no, we're just moving to a better new version of the database or whatever, and super breezy, no problem, they have other things to do. And now you have to have that discussion. Services allow you to separate those things. And of course, that means that there's always a concern for siloing, but if you have really good management, coordination, and you're working on your communication between things, it can be resolved and okay. Also, when you're doing service-oriented architectures, you really want to work really hard to standardize. Every time you have like a new run, like you certainly just shouldn't have like one language that you write everything in. That's a horrible idea because things you actually, like JavaScript doesn't have int 64s or byte arrays, so why would you use it for search? Like those just don't, like, it's not a thing. I hope I didn't just call somebody out accidentally. But you want to pick like some standard ways of communicating between your systems, not the full fat client stuff, but like dumb clients that are like how you do RPC and they expose the same kind of metrics. And when you want to add a metric, it's pretty easy. And then the systems who want to add more stuff, they add more stuff in their place, and then eventually maybe get wrapped up in the core library, that kind of stuff. You pick a metrics library that exposes things over like some port. Maybe you pick like HTTP and it sends out JSON, like your collectors all go to that, and yada, 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 yada. And that means that you can scale out all this stuff without, you only have to write a thing once. And of course, that gets more important as you go bigger, but I would argue that it is critical even at a small company because you don't actually have time to like figure out your like Haskell friend's code and like how he did metrics and then figure out how to like take a dump of its heap. And I say this, I'm saying a lot of JVM-based stuff, but this doesn't just apply to JVM. Like I write C++ now and yada, yada, yada. So it's a whole thing. On-call rotations. Oh man, I'm down to a couple minutes. On-call rotations are awesome. You should have an actual defined time you start to be on call and when you stop to be on call. Otherwise, everybody's on call, and then you all start flipping switches all at once, and now nobody can tell what's happening because we've all been flipping switches all on our own. You need some way to coordinate this, and also the psychological effect of having an on-call rotation means that you only have to really stress out, or at least not drink as much, for like a day or a week, versus like all the time and never knowing. It also means that there's like some responsibility that you build in. I know that because I was the Notorious E.O.C, which is one of the engineers on call for all of Twitter in into 2009, all of 2010, and it was a shit show. It was really hard, and we did not start understanding our systems until we started splitting up, not only having a decent call rotation, but also splitting up the on-call rotations to the particular systems that people were experienced in.
This was a big deal for us at Twitter because we were very much of the mind that everybody should feel like they own all of the code. But as you start writing more systems, it becomes impossible to track all the changes in each system. It's impossible to know where all those machines are. Very few people have that overview, and mostly they spend all their time, writing emails. So you split up responsibilities. You figure out what can happen. You figure out like the timing for those things. Now PagerDuty exists, so you don't have to write your own software to do it. You can just use PagerDuty, and it gives you this stuff. It's great. OK, and now in my last minute or so, we're going to do it. I'm going to increase the size of my thought leadership. I've been talking mostly technical stuff with some hints of social, and now I'm going to do a little bit about social stuff. The first is that robust distributed systems cost more than single machine systems. They just require more capital. Why do they require more capital? Well, the key word is robust. Distributed system state spaces are much, much larger than single machine systems. The failure modes are greater, as we talked about before. There are more kinds of failures, and they happen more often. You also have, and so at a certain point, you actually need the capital to build out enough machines to see the bugs that only show up when you have some number of machines. That's just a thing. You can kind of fake it with VMs and do some craziness, but at a certain point, but the problem with the VMs is that you also have bugs that only show up at when we have enough data that doesn't fit onto a single machine. When you cross over the 2 to the 53-bit number into the 64 bits, or 64-bit into undefined 64 bits, there are things that only show up there. There are bugs, there are use cases that you think you have covered, but don't exist until you're in prod. And doing stuff in prod takes money, because you actually need to keep it up. It needs replication, and it needs all these other things. So it takes money to do this. And so what that means, though, is that robust open source distributed systems are less common, because open source folks are typically very, very few open source projects have the capital to spend to A, have your systems up on a number of machines, not a huge amount, but a number of machines, B, keep them up for long periods of time, because that turns out to be a source of bugs. If you're just so rock solid that you stay up for you don't touch it for weeks, there can be crashes that happen after 2 weeks. Those are pretty common, actually. And 3, they don't typically have any source of production-y data. They don't have flowing data happening through it all the time. They have usually random or fake data at best. But I don't know of an open source project without significant funding that is able to pull off all these 3. This is maybe a couple. And so that's interesting, and we need to figure that out, because I don't know how we're going to continue doing this stuff the way we are today. OK. And then the last thing is that collaboration is politics. I am sick and tired of hearing software engineers say something is political and therefore bad. It turns out when you have 2 people in a room, you have politics. Because politics is when you are agreeing on things. And sometimes it's easier to have those politics, and sometimes they're more difficult. And you have good politics, and you have bad politics. But you actually just have to agree on things. We think of ourselves as rational human beings, that we are making reasoned, objective ideas. But if you actually look at most of our decision making, maybe even especially in small groups, those decision makings are not rational. They're being made off emotions and trust and how much and this kind of scar tissue that we've seen from previous systems. And we need to respect that and understand that. We work in distributed systems, which means that we tend to be on larger teams. We tend to work in larger companies. So that means this problem gets even worse. But what's interesting is we're willing to talk about consensus protocols, and we're willing to talk about communications between machines, but we're so not OK with doing that same work to talk to another engineer, to talk to a PM, to talk to a user. I think we need to flip that a little bit. OK. That's it. That's all I've got. And there are some links here that I can't show you. Well, fuck it. Apparently, one of the links was from my internal talk at the top that you can't read, but good luck. There's also a couple of links that I think you should read. I directly stole stuff from Coda Hale's metrics everywhere, including the mental gap thing. There's a fallacy of distributed computing explained, which is fantastic. There is Jeff Dean's
keynote that one of the slides is numbers everyone should know, which is like in nanoseconds, how long does an L1 cache blowout take? How long does main memory disk going across the US, going to Amsterdam across the network? It's pretty good. Also, about a year and a couple of months ago, I wrote a blog post that was the basis of some of this talk, but it goes into a lot more at the very end. Notes on distributed systems for youngbloods. And now, I will take questions. Hey, what's up? Oh, can we get a, yeah, we're gonna do a microphone. Hold on a second. Because they're telling me to like repeat the question. I'm not gonna do that.
So you touched on metrics a number of times.
Yeah.
And I know there are gonna be a million answers to this, but do you have any recommendations on recording and publishing metrics, like technologies that you use, things that have succeeded?
Yep. So Twitter has written 2. I kind of recommend the newer one. Well, sort of. There's if you look in the Finagle stuff, there's a thing called metrics. That's a good library. Coda Hale actually wrote a library called metrics, which is really, really good. It's really good. There's aggregation problems in all of these. There's a really crappy one that we wrote a while ago. Well, it wasn't crappy at the time, but now it's crappy because the systems have evolved. This thing called ostrich. But basically, you can't go wrong with something that just exposes an HTTP endpoint that you can curl on the machine, and some JSON and some numbers, and just go to town. But Coda Hale's metrics is really good. The Finagle stuff is also good. We use it a lot. I mean, that's the basis of all of our metrics. Yeah. All right. Cool. Boom. I will repeat the question if we can't get to it, but
okay.
It's funny.
So I have 2 questions. The first one is, what is the average lifespan of systems in Twitter?
Average lifespan. You mean, I'm guessing you do not mean how often do we restart a process, but you're guessing how long do we wait before we rewrite it?
Yes.
So I think we're still a little too early to give you really solid numbers, but numbers that I've heard from like my Goog friends are about 18 months to 24, something like that. Okay. Before they just something breaks and they have to redo it. Certainly that's about the right timeline for TFE, because we keep having to take sections of it and just completely redo it. That's one of the reasons it's now a 2-process architecture, and we're now turning that front end and we're doing magic. So I'm writing a lot of C++ right now. And that's about right for having to replace a system whole cloth. And it gets a lot easier when you're doing partial rollouts and stuff like that, once you got a feature flag. What's interesting is a lot of these things that you would consider the death of a system stop looking like the death of a system. They start becoming slow migrations, other systems just take over pieces of it, and you start moving those things over. So it never looks like a full rewrite, and it never quite looks like you're killing off a system, though sometimes explicitly you are. So it's harder to there's a gray area. But it's about, I would say, given the data that we have at Twitter, I think the Google number is about right. I'm not saying Google said this, I'm just saying that I heard this from some people. That's about 18 months, 24 months, something like that.
And what kind of technologies you use to develop software?
So at Twitter, we use a variety. We have standardized, most of our systems are on the JVM, Java and Scala. We also are writing C++, like I mentioned, I'm doing that right now. We got a little C, because we have some kernel hackers and yada yada. We also have, for build tools and stuff like that, we have some Python. Of course, we have Ruby. Some of our build tools, unfortunately, deal with JavaScript, so we have some NPM, Node stuff. But we have a variety of things like that. So if you're talking about languages, now we're talking about runtime. Runtime, Hadoop, is a huge portion of our stack. We use Pig, and we are big contributors back to that Pig project. We have, Cassandra's no longer a thing, but we use Finagle a lot for our RPC. That's our standard. I don't like Finagle very much, but it's a standard, and so it's awesome. I don't care. I don't care if I don't like the API. Fuck it. Because it's actually standard and everybody just uses it. And it's great. That means I can know how everybody's systems work. It's awesome. Yeah.
Thank you.
Word. OK, cool. I'll repeat questions then. Anybody else? Yes?
So the splitting up services.
Yep.
Interconnectedness?
OK, so you're saying that the way we're splitting up services, it sounds like there's a very heterogeneous and everything gets split up.
My question was basically about coupling. So if you end up with the coupling between a lot of parts of a heterogeneous system, how do you resolve the software development lifecycle? You end up with problems because you have ripple effects to changes. Or do I have your system not characterized correctly?
No. I think I get where you're trying to get at, which is, so you're worried about coupling between systems. I'm not sure that I guess maybe I don't completely understand the question. We haven't run into issues where a bunch of knock-on effects ripple through the entire system. It has been relatively rare that we have to change everything because we changed how the user's database works, because the API remains the same. And so if the user services API has to change, because it has to change, which I think we've done maybe once, you have to fix a bunch of different systems, but you do that over time, and you have a stat saying how many people are using the old API versus the new one, and then and you continue forward with that.
That's the answer, basically.
Yeah, right. So in distributed systems, this is a topic that I have wanted to breach. Basically, the idea is that APIs become much more critical, and you have to build ones that are fairly well extendable. And in Thrift, I actually really like Thrift. You can talk shit about Thrift all day long. What I like about Thrift is that you can add optional things at the end, but you can't change the method name without breaking everybody else's client. And that's cool. And you can't change the return type whole cloth without somebody complaining at you, which is good, because that's actually how we need to be treating APIs. This is the same reason why Twitter is still on API v1.1, even though we would really like to change how the timelines API works. But we can't just change the timeline API and break everybody's app. We have to make a new one and then change how it works. Which, by the way, here's how timelines should work that we've all agreed upon. You have a list of IDs, and you have maybe an optional objects hash over to the side, in the JSON object next door. So you get the tweet IDs, and then maybe some optional objects that are tweet objects that would match some of those tweet IDs that we think you're going to query for anyways. That's how it should work, because that's really cacheable and easy and nice, instead of having to decompose and do all these user object things that are included in the timeline. Anyway, got a whole thing. All right, anybody else? Yeah. Oh. Where are we going? Was it you? No?
Hands?
I think there was a hand over here. We're gonna, the man sitting down over there. Hey, what's up? Thank you you're very tall, so I'm glad that you're sitting down.
Yes. Thank you. I was wondering, you mentioned extracting services.
Yes.
Do you mean that in the same sense that people might refactor code by extracting method?
Boom. Yes.
Okay.
You actually, yeah. Though it's usually at a more abstract level. It's okay, what behaviors and requests are we going to have served by this other service? Containerized and moved over. Yeah, right. And so the question that you haven't asked, and I'm going to take this opportunity to say it because I didn't say it in my talk. Thank you very much. You will get a lot of questions, especially inside your team, saying, well, how big should a service be? And you'll say, smaller than the current ones we have. And they'll go, no, really, dude. And you're like, well, let's talk about how big a unit test should be. What is a unit, right? How big should an object be? And there is a bunch of things that you can reason about. Well, okay, so it should be related methods, and so maybe we'll have the user service over here. And then there's some gray areas. Okay, well maybe the session handling login stuff should also be on that object because it deals with the user stuff. But then everybody has to query this thing for all the HTTP stuff, and you want to scale it out that way. So maybe we'll just put it in as a separate service later. But it's an organic, ongoing process, and it's one that is bounded not totally by technical boundaries. The constraints are not purely technical, they are also social. They're what teams are involved and what they're willing to do. I will say that the easier you make it to deploy services, the better off you will be, because then you can cross social boundaries much easier.
A lot closer to Conway's law.
A lot closer to Conway's law, yes. Yeah. And so you got, yes, the whole thing. Anybody else? Yeah.
So I was wondering, do you have any recommendations on the best way to support a distributed system and deploying these distributed systems through multiple environments? Is there any way that, because that seems to be where it gets pretty complex.
Yeah, and I will tell you that a lot of companies that do this stuff, they mostly punt in the ways that people think are interesting and good. There comes a certain point where you can't actually duplicate state from the production environment to a staging environment without literally buying the same amount of hardware and doubling all of your costs. Just can't happen. You can certainly do things where you replicate some of the data over and create a fake staging environment that you can do this in. But mostly what you're going to do is you're going to try to make it as cheap and easy to deploy a fake version of those things in place.
And sometimes you'll just stub it out. And sometimes those staging environment things will query production data. And you've got to be really careful and trust your engineers. And you've got to have good stats and auditing trails and yada, yada, yada. But it's not a huge, massive deal. You just do it. What we do have is we have staging environments that you can go to certain domains that look like Twitter, or like the various subsystems that make up what twitter.com is. And so TFE, one of its roles is actually providing the pattern matching to actually send requests to certain domains, paths, HTTP paths, and like authentication states and decider values, and we figure out which set of machines it should go to and be satisfied by. Building out one of those tends to be really helpful, because then you can just like deploy configs for the staging environments, and they go to completely separate instances of things. I am, of course, thinking in terms of web apps, and that is where I spend a lot of time in. You run up against cost. And so you have to start figure out how to be responsible engineers in production. But you can totally fake out and do some staging stuff that is absolutely critical because you need to know what it looks like in a browser, that kind of stuff. But yeah, I guess that was an answer. I hope that helped. Good luck. It's an open problem. Let me put it that way. Open problem, nobody's really solved it. They're all kind of like hacked up. I think we're out of time probably. Yeah? Anybody? Oh, I can just get to decide. All right, fine. We're done. Have fun, guys.